Hi, now you've seen this little baby in several previous videos, the Rohde Schwarz HMO1202 series scopes, and click here if you want to have a look at I've done a teardown video of this thing. I've also done videos for comparing the FFT mode, which I really like on this thing, and things like that. It's a really nice little compact professional scope, so there's really a lot to love about this thing. It's whisper quiet, it's small and compact, one of the smallest scopes on the market, and it's great and responsive and fast and everything else, and it's fairly decent value for a real top shelf brand like Rohde Schwarz. And it's a mixed signal scope, of course, and probably its only major downside is that it's only 2 channels, but hey, it's for this sort of compact scope, it's just fine. So I love this little thing, and you'll notice that up the top here, it does not have a bandwidth listed on it, which is quite unusual, and the reason they do that is because this is a software upgradable bandwidth scope, as many on the market are nowadays. Probably a good majority of them actually have the full bandwidth inside them in the vertical amplifiers here. The bandwidth is actually there, but then they software limit you via license keys and everything else to various bandwidths. Now this one is available in 100 megahertz as the base bandwidth. That's about current price is about $1,300 for that one, and there's also a 200 megahertz version, and my one here is the 300 megahertz version, but you wouldn't know it by looking at the front panel, because it's just a license key inside which upgrades the bandwidth. So even the base model 100 megahertz unit you buy for $1,200-$1,300 or something like that has the full 300 megahertz bandwidth in here. So I thought, just for educational purposes, we will crack this thing open yet again, and we'll have a look at the front end here yet again and see what chip it's using, what topology it's using, and see if there's any little tweaks that we can make to potentially get greater bandwidth out of the base model unit. Unfortunately, I've actually got, in quote marks, I've got the 300 megahertz, the license keys already installed for this one. It is full bandwidth, but we should be able to probe some things and have a look at how they're actually doing that. Should be fun. Let's go. And the only thing that tells me this is a 300 megahertz version is just this sticker on the back they've got here. So this is done at the factory. They've whacked the sticker on, but you can actually buy the license upgrade later. So here's inside the unit. As we've seen in the previous teardown video, I've got metal cans on the top here for our 2 analog channels, and unfortunately metal cans on the bottom, which are even more unfortunately soldered in place. But there's only one point there, one solder point, so I can desolder that and lift this can off without having to take the board out. So yeah, okay, small win. Now if we have a look at the front end here, I've got that bottom side can off. Then there's our BNC. We've got some attenuation switch-in relays, and these transistors down in here, they're probably, they're those SOT23 packages. They're likely transistors. They're probably the JFET front end, probably a couple of JFETs and a BJT or something like that. And apart from that, I've got here's a photo of the other side of the board. I won't bother taking the other side of the board. I think you have to get the whole board out to get that out. Yeah, I've got a photo of that side, and there's nothing terribly interesting there. The part we are interested in is, however, right here. That puppy. That's doing all the business. And here it is. Sorry about the angle, but it's hard to read this number if you don't get the light at the right angle. It's a 6518, and this is quite a common part. You'll find these in a lot of scopes on the market, and we'll see that this might be doing some magic. Let's go to the data sheet. So here we go, the LMH6518 900 megahertz digitally programmable VGA. That's not video graphics adapter, that's variable gain amplifier. And this is specifically, look, it tells you oscilloscope programmable gain amplifier. And this is the internal block diagram. There's an input preamp, there's a ladder attenuator, which should be being used most likely is being used by the volts per division setting, so we'll be checking that here today as well. But look, bandwidth limiting circuit right inside there. There it is. That's what we're interested in. And it's got a differential output driver. So differential input, differential output there. And it's got an auxiliary output also tapped off here, which you can use for triggering as well. So that's very handy to, when you select channel 1 triggering, it's most likely going to be coming from here. So we can actually go down. There's all sorts of jazz here, 900 megahertz, blah, blah, blah. We won't go through all the specs, which are quite impressive. It's a very nice part, perfect for scope front ends. Here's our pin out. So we're actually looking, what we want to do is tap into the serial line on this thing, the SPI line. So here they are. Chip select, SDIO, and S-clock there. So those 3 pins 9, 10, and 11, they're the ones we want to tap into to see. Oh, by the way, here are the various responses for the different attenuation settings, which we'll see. So if we go down here, they've got very comprehensive parametric graphs there. I like it. That's terrific. And but what we want to do is see down here. Here's the signal path, the ladder step attenuator, no problems whatsoever. As I said, the volts per division setting is probably doing that. Front end attenuators, and we're getting down here. Trust me, here comes the exciting part. It's coming. I know it is. And there's an example, digital oscilloscope front end. So maybe that's, they might have used this as an example of how to do this, but they've been designing scopes for a long time. They would have their own implementation. So here's the SPI pins. It's 3-wire SPI interface. Here's the serial protocol stuff, which we'll no doubt have a look at. But here it is, table 6, the filter selection data field. And these are the bandwidths. Look, you can actually choose full bandwidth if you write 000 to a register somewhere in the chip, or you can get 750, 650, 350, not quite the 300 megahertz maximum bandwidth which this one has. So the bandwidth is most likely being limited somewhere else. Here's the theory, but the 200 megahertz and 100 megahertz bandwidths, bingo, they sell 100 megahertz and 200 megahertz versions of this scope, software license upgradable. So you can bet your bottom dollar all they're doing is setting a couple of registers inside this chip. You buy your license code, you plug it in, and it says, yep, you now got 200 megahertz, for example. All they're doing is setting just changing a couple of bits in a register there, which limits the bandwidth inside that front end chip, because they've already gone to all the expense and effort to design the 300 megahertz bandwidth front end and characterize it and everything else. It doesn't make sense to really build a scope that has a physical 100 megahertz limitation. So these companies, very common these days, they actually build the bandwidth into the scope and then software limit the options. And they do that in this case using a chip, whereas I think one of the early Rigol ones, whereas the GS1052E was it, or could be the 1054Z as well, I forget. But yeah, it's using like a Varicap diode and then uses a digital line to drive that, and it sort of sets a bandwidth limit and, that sort of stuff. So this one uses a specific chip which has a digitally programmable filter, analog filter. It's not a digital filter, analog filter built in. And all they do is flipping those bits. So that's what we're going to try today. We're going to probe that bus and see if those bits pop out. I bet you they will. So this is real easy to find. Here we go. Pin 1 here, and 4 pins per side, exactly as per the data sheet. 1, 2, 3, 4, 5, 6, 7, 8 on that side, and bingo, 9, 10, 11. And look, they go out to convenient vias there so that we can put some little mod wire in. They're like difficult to probe. Like yes, you can probe them with your scope, but trying to hold 3 on there at once is, it's ridiculous. So yeah, what we'll do is we'll solder some little, 35 gauge mod wire or something on there, and we'll be able to then crack into that with our logic analyzer and see what's going on. That'll be fun. And of course, this will apply to any scope on the market that uses the LMH6518. And if your scope does use this chip in the front end, and it's got like selectable bandwidth, then you can bet your bottom dollar that that's how they're doing the bandwidth limiting in this thing, because this thing has, as we saw on the datasheet, the 20 megahertz bandwidth limit. So practically every scope has a 20 megahertz bandwidth limit, and this is almost certainly how they're doing it if they have this chip. Just send an SPI command in, bingo, you've got your 20 megahertz bandwidth limit, and it's most likely how they're doing the bandwidth, the software license upgradable bandwidth as well. But in this case, this is a 300 megahertz scope, but this specific bandwidth option inside this chip is 350 megahertz. The filter, that's the filter figure in there. So they're most likely doing that, or the rest of the circuitry could actually be limited to 300 megahertz. It may not actually be the chip, but you can bet your bottom dollar that the 200 megahertz software option is going to enable the 200 megahertz limit inside this chip. So I'll do this using my Tagano microscope here, and yes, I've got to prop it up on some books, so why not prop it up on the Art of Electronics? Beauty. So yeah, because it can't, it's got a big working distance, but of course you can't have it flat on the bench and be this high up. It just, the working distance doesn't work there. So I've got my little remote control and we can zoom in. Yay! Excellent. Of course, for actually doing a small job like this, it's still not as good as my Mantis Elite microscope here. Like, you know, you can't beat that 3D, you know, the actual 3D stereoscopic effect of that. And yes, this can record video, but as you've seen, it's pretty crap. So we'll use the Tagano and see. It's blocking a bit of the light here. It's just got one light source here. So I've got my maximum lab lights on here. So, you know, get a little bit of noise in the image and stuff like that. And I can capture the HDMI output. So let's give it a go. All right, check out the range of zoom that we've got here. Here's my hand and there's our little chippy. We can zoom all the way in. Look at that. Absolutely beautiful, this thing. And get the big working distance. Alright, we're going to use some 30 AWG wire wrap wire. Should do the job, otherwise known as mod wire, hack wire, whatever you want to call it. Let's go. And you might think this tip is ginormous. You want to be able to get in there and get heat on that joint right down in. Oh, can we see some? Where was that heat coming up from the soldering iron? Yes, distorting the image. And what I'll do is I'll just practice somewhere else first, just to see if the wire can go down through the via here. Although we don't have to actually go down, but that creates a stronger mechanical bond. So I don't know. Let's try this pad here. Perhaps I got a little bit of solder on the bottom. No, I think that solder mask coming over the pads, it's almost not quite tented. It's like, you know, 10-20% tented, which is really rather annoying. Yeah, we can access the pad, but yeah, having a hard time getting that iron onto it, so we might actually have to go for a sharper, more conical tip to actually get right in there. So let's give this one a whirl. It's not often that I use the conical point tips. So this is the, for those playing along at home, that's the JBC tip I'm going to use now. This is not easy. These are tiny vias and there's not much, you know, you can scrape away the tracks and, you know, stuff like that to get into it. But yeah, anyway, it's taken far too long. So we'll just whack some flux around that chip there. This is all really fine pitch stuff. You'd have a hard time doing this without magnification. Although, you know, I've done this stuff before without it, but yeah, it's just a real pain in the ass. But yeah, I don't like our chances of getting down those vias. I think our 30, I think this is the smallest I've got, the 30 AWG. So what I'll do is I'll just scrape away some of that solder mask first, just so that I can get more iron contact onto the pad, which then can maybe solder the wire onto. Let's give that a whirl. This could get messy. It looks ugly, but then you clean it up and it looks just fine. There we go. I think we got one. Don't like my chances of putting it down the hole, but that's okay. We'll just tack it there onto the pad. She'll be right. I stripped a bit too much off there, I think. And just apply a dab of flux again each time, just to make your life easier. And bingo, we've got some more solder in there. By the way, with this fine conical tip, you're going to want to turn the temperature up. I've currently got it set to 325. Whereas fine stuff like this I'd normally do with my wedge and things like that at like 275, 270, something like even 265, something like that. But because, the physical surface area is not there, then, you might have to turn your temp up a bit. But I've found just a little experiment that, I've had to, up the temperature just a bit. This is why you need a temperature-controlled soldering iron. Every job is different. My big fat fingers don't get in the way. That'll do. That's good enough. That's a bit nasty, but there we go. I think she flowed. Yes, I did tin these wires beforehand. They do come tinned. They're tinned tinned wire wrapping wire. But yeah, you just want to put a fresh coat on there and don't have a big blob. You just want to have put a big blob on and then use your iron to take it back off, and there you go. Oh, the top one's dodgy as. Let me redo that. And we'll just clean that up a little bit, and that will evaporate and she'll be right. No worries. And I've deliberately left these wires long so you can handle the ends of them, put your probes on, get them off the board and things like that, because signal integrity is not a big issue here, and allows us to put some tape on there. You definitely want to put some tape down on there so that when you handle these leads on the other end, there's no stress on those leads. So you can get down here, hook up your probes and wiggle them around, no problems whatsoever. Move the thing around the bench, and you're not going to break your little tiny little joint in there. And of course that wouldn't have been an issue if we could have got these like down the via properly, and then it would have had real, a lot of mechanical strength. And we probably could have got in there with a smaller gauge, like a multi strand wire like this, and we could have got in there and used smaller stuff like that. Maybe got down the via, but it doesn't matter. This is more than good enough. We just want to probe it. It's not like a permanent fix or anything. And I can't think of anything more appropriate than to use the scope itself to probe its own clacker right up the back. And we can do this because there's no ground reference problems, because we can check that by looking at the logic analyzer ground like this, and there we go. And the ground on the PCB down in there it's all a common ground, so we won't even need a ground. We won't even need to hook up the ground probes for it. Everything could be hunky-dory. We can probe that safely. The signal integrity is not going to be terrific, but who cares? It's just an SPI bus. So let's boot her on and see what we get. There is no back on the scope. It's all safe. All the mains, power supply, everything is inside the shielded and earth case, so no worries whatsoever. So let's give it a whirl. But you'll notice that channel 2 is picking up some 50 hertz hum here, because we've taken the can off, it's unshielded, and we've hooked up lines in there. Everything's capacitively coupling all over the place, and yeah, that's interesting. So we have to turn on our bus here, configure, we've got SPI, and then we can configure the chip select, the clock, and the data lines. And as you can see, we can choose which channel we want there. We can use the analog channels, or we can use the digital channels. In this case, I could have used the analog channels, but as you saw, we're sort of hacking into channel 2 there. So, I better try and figure out which one's what. All right, so we're probing up its own clacker here, and I've got the bus and the logic analyzer set at the same time, so that's why we're getting duplicate waveforms here. And I've got channel 1 also set up to the SPI clock line, and if we single shot capture this works a bit bizarrely. It's quite frustrating at first, the trigger system on this. If you want to go into single shot mode, you've got to push single, and then it has this horizontal stop, run stop one here, and then you've got to actually disable that to then get the waveform running. Anyway, if we go down here, we can actually see, the data line SPI lines. Actually, they're not doing anything at the moment, so this is like a live pulse view. This is like a, you've got like 8 real logic analyzers, old school logic analyzers there that, regardless of your sampling mode, will show you what's happening there. So that SPI line is doing nothing at the moment. So it's not polled regularly at all. But if I go into channel 2 and I'm going to hit the bandwidth button here, the bandwidth limit, which should send an SPI command through to that chip on that second channel, right? So that LMH chip. So let's hit that, and we should see the SPI line pulse. And bingo, we did, and we actually saw our waveform recapture. So there we go. We can get it to do that. But interestingly, I also found, watch this, if I watch these lines here, right, it's ordinarily doing nothing. If I go into single shot mode, okay, it did that. But once I hit this, it actually sends the SPI command to that chip as well. Watch it. Boom. There it goes. Very interesting. So it's not just when you change the bandwidth, it's when you do other oscilloscope modes and things like that, that it actually, it's some point in the code where it goes, oh, okay, I'll just resend the command out to the front end chip on channel 2. Presumably it's sending it to both channel 1 and channel 2 chips. It sort of like refreshes them or whatever. So that's just, that's just a quirk in the code, or maybe there's some, functional reasoning behind that. But yeah, it's not ordinarily polled like this. Now check this out. This is interesting. What we've got here is the second line here. There is no chip select up here, by the way. Channel 0 up there is supposed to be the chip select line, so it's just permanently high. So there must be something wrong with my connection or something, because the chip needs chip select low, and it should ordinarily pulse, but there's nothing there. So anyway, we'll solve that later. I just wanted to show you. So the second one is the clock line, and the third one is the data line there. And if we go in, look at the data line here. There's these odd little oddball pulses, and on the clock as well. So if we actually go in and because ordinarily it'll clock on the positive edge. It'll clock the data on the positive edge of the clock here. So if we go and have a look, there's the positive edge of our clock, boom, and then a little bit after that, just a couple of samples after, there's a little tiny transition there on the data line. Now, this is obviously not part of the regular SPI protocol. I don't believe it's real, so this should ring alarm bells when you see like little pulses like that. So, little short, narrow pulses, that should not be there. It should be data following the clock. The highest frequency thing on here should be this clock line on the second channel here. So we're getting a problem, and that almost certainly has to be a signal integrity problem. So I've got actually no ground hooked up at the moment from the logic probe, because as we said before, in theory you shouldn't need it, but it looks like in practice we're going to need it. So I'm going to hook that back up and re-trigger it. All right, so what I've done is just hooked a ground line on just one of them, the clock line, up to the shield of one of the cans there. Near enough. There wasn't any other convenient points. So let's re-trigger that and see what we get here. There we go. It just vanished. It just vanished. There you go. So it did need that ground. Yep, I can't see any others on there at all. So once again, I can push the bandwidth limit button. I've got it in normal mode at the moment. It's triggering on the first negative edge of the channel 1 clock here. I haven't bothered triggering off any commands or anything like that. So yeah, we can just hit that bandwidth button, and of course it sends a trigger, or it sends a command through to our SPI bus, which then sends the data again, and we just re-trigger. So we can just capture to our heart's content like that. Nice. And if you're curious to see what it actually sends, well, that's basically it. And by the way, you can see the noise coupling into the second channel there. So because we've got it unshielded and we're actually probing the things, there's capacitive coupling going on to some high impedance node or something like that there. So we can do that, and we can trigger, and so that's all it sends. That's basically the entire data that it sends when you switch the bandwidth limit mode or you do some other mode which causes it to refresh the data, that is the commands that are resent through to that bandwidth limit slash gain chip. I'll tell you what, I really like how they've got the triggering set up here. I've got the trigger manual set to the logic source, so you can go in here, set it to the logic source like this, and then you select it. And I just like the diagram there. It shows you and which channels and the threshold voltages and whether it goes true. Brilliant. Now with this chip select line here, I actually took it back under the microscope, checked it, I buzzed it out, it was making connection. I even used a different channel, the fourth channel down here, D3, on the logic analyzer, and still nothing. So I don't know what that chip select line is doing. It's almost as if it doesn't transition, it stays high. So that chip is like disabled. Like, what the? Like, I don't know. Like, it can't be. So something is still seriously wrong there anyway. And I can change the vertical for channel 2, for example, which should also eventually re-trigger that. But it doesn't. It doesn't, which is interesting. That is fascinating. That is really fascinating. Why doesn't it do that? I'm changing channel 2. But if we do the bandwidth limit, it definitely re-triggers and sends that SPI packet to there. Now, anyway, there are two different parts to this. By the way, I showed that before. That's basically the only thing that we capture there. And it's got this one here, and it's got this one here. Now, this one here is 24 bits long. It's exactly what it shows in the datasheet. So if we have a look here at the write operation, you can see that this is a single access cycle, and the chip select is supposed to go low, of course, but it doesn't, so we're not sure what's going on there. And this shows that the data bits are sampled on the positive going edge of the S clock here, and it shows that there's 24 bits total in there. So that's exactly what I counted in there. So there's a command field of 8 bits. So there's 8 bits command and 16 bits data. And here is that 16-bit data field, and you can see D6, D7, D8 here, C table 6, ta-da! And this is the bit that should change. So I'd expect a D6 to change from 20 to this bit to change from 20 to 350. So D8 and D6, I'd expect those to toggle on the different write operations when we toggle that bandwidth limit button off and on, or at least go between 1 and 0 here, between 20 and full, for example. So, yeah, but we're not seeing that. We're seeing no data change at all. It's weird. Now, there's something very, very strange going on here. I just know that chip select line must be pulsing. So what I've done is I've hooked up a second scope here, and sure enough, to the chip select line, look, there it is. I can re-trigger. Here we go. I'll show you in the one shot. I'll re-trigger this thing. Oh, here we go. Single shot capture. Okay. So and I press the bandwidth limit button. Bingo. There's the chip select line. I'm probing it, and I'm probing the exact same line on the Rohde Schwarz scope itself, and it's just like it's not doing anything. It's not doing anything. Look. Type, trigger, edge, no worries. Source, channel 1, we're in channel 1. Negative slope, positive negative slope, doesn't matter. It should capture something, and it's not capturing a damn thing. Doesn't help that the single mode works back to front. It's really weird. Anyway, auto normal thing, like, it stays high. That's it. What the hell? I've changed probes to the genuine HMEG/Rohde Schwarz one, and it's the same thing, but this is the data line now. I was getting the same thing on chip select, just wasn't there, and now I'm getting this on the data line, which coincidentally is just continuously triggering now. So, yeah, go figure, but you put it in, let's go over to channel 1 here, it still triggers. Let's go into, I don't know, another menu. It's still automatically triggering, whereas we weren't seeing that before. But something's weird going on. This thing just will not probe the chip select line for some bizarre reason. And here's this average trap that I did in a previous video just recently. If I actually trigger this thing, here we go. This is my chip select line, and you'll think, oh, something weird's happening to the chip select line, but it's not. I guarantee you, if I go over here, silly me, it's still got averaging mode on. I was just playing around with that this morning. Somebody asked if I could do that. Anyway, here we go. There we go. There's our chip select line. It's not continuous. The chip select line is not continuously triggering. Okay, so you'll see it's not updating there at all. But if I press the bandwidth limit button, bingo, it updates, and then it just updated again, and so it's like, but that data on the data line just keeps coming out. So this has got to be a PEBCAC. I'm just trying to sanity check to figure out what's going on here. Sorry about all this. This is like real time, this is a real problem I'm encountering here, so I'm going to show it. And look, I'm probing the data line on both of them, so it's like it's auto-updating, no problems whatsoever, right? Everything's fine. For whatever reason, it's auto-updating at the moment, or sending data on that line, although there's no chip select there. So I've got both probes on exactly the same point with two scopes. Let me now do that exact same thing, but move the probes to the chip select line. I'm pressing the bandwidth limit button there. Okay, I've got both scopes set to normal mode, so it will only trigger. You'll notice there's small changes in the width of that, but I'm getting nothing there. I swear I'm probing exactly the same damn point down there. There's the probes. Look. Probing exactly the same point. And, like, what? What? That is one of the weirdest things that I've ever seen. It's not like this scope is incapable of probing itself. The analog front end does not matter. It should not matter. It can't matter where it's hooked up to, as long as, you don't short anything out with ground issues or anything like that. I'm going to the chassis ground. It shouldn't care where the signal is coming from. It's relative to that ground. It's exactly the same point. It should work, and it works for one of the lines on the SPA bus, but it doesn't work on the other. What? There's got to be some sort of PEBCAC with this thing. It's got to be me. What the hell am I doing? I've resorted to the manual. This is bad. It really is. I don't know what's going on with this scope. No, I'm at a loss here. Look, I've got the correct type. I've got edge triggering. I'm the correct source, channel 1, which is what I'm using. The slope, positive, negative, both. It makes absolutely no difference to what happens. And then the filter, we're on DC. So we can set our level here, okay? And here is the thing, right? We put it in auto mode, okay? So here's our level. It's positive. Trigger level is smack in the middle, right? Here's our ground point down here. Everything's hunky-dory. This should work. You put in normal mode, okay? The trigger goes like this. And if I go to channel 2 here and change the bandwidth, look, it triggered, but it didn't capture and display any data. What the hell is going on? Yet, if I go over to my Keysight scope here and I do the same normal mode and I press that bandwidth limit button, it's capturing that. The probes are on the exact same point. There is something seriously wrong with this scope, and I don't know what. Have I got some sort of weird software bug? If I have, it's bloody well major. People are probably screaming at me right now. Oh, it's obvious, but unbelievable. Okay, so it's clearly this trigger thing here is resetting. Whenever I push this bandwidth limit, I can actually disconnect my input here, right? We just triggered. And I can push this bandwidth limit and it resets that. So, and there's no triggered light here, which is like a latched, a pulse stretched triggered light. So it's obvious. It is not triggering, right? So, okay, it's not triggering. That's why our data is not coming up. Okay, fair enough. But why the hell is it not triggering? That signal is there. Look, here we go. Look, I'll plug this same thing over to here, okay, and let's do the bandwidth thing. There we go. Look at that. Okay, so that needs compensation, obviously. That's, you know, it's poorly compensated, but it works. Yet, I plug it on this scope and it doesn't. And the exact same thing happens on channel 2 when I set the source to there and I've set it up. And look, if I actually plug in a signal here, there we go, I'm plugging in like a 1 megahertz square wave, it triggers. No problems at all. And like if I go back to channel 1, it's there. So bugger it, I've had enough of using this thing to probe its own clacker. Let's have a look now at hooking up the SPI line here. So I've got all 3 channels coming in. By the way, it is not a true SPI as you know it, because SPI, if we go in here, is normally a 4-wire thing. We've got our clock, our bloody touchscreen, our MOSI and our MISO, i.e. Input and output data signals and chip select. But in this case, it's actually a 3-wire SPI interface. It's still SPI, but it's 3-wire, so it shares, it's bi-directional here, so it's not as great a throughput, it goes tri-state and everything else. So anyway, we don't actually have specific support for that, so I've just set it up here. Haven't set up the bits yet, but let's just trigger this thing and have a look. I'll press the bandwidth button and bam, there we go. Look at this. We've got our clock, we've got our data, and now we have our chip select. Yay! Now the most interesting thing about this is, look, we're getting our 24 clocks, exactly what we expect before. And if I zoom right out, okay, just what we were doing way back, and I press it, look, we're getting none of that double rubbish that we were getting before. You remember the one that had the 50 or 60 clocks or whatever? We're getting exactly what we expect as per the data sheet. So it's bizarre. I got no idea. This is exactly what we expect. And let's just have a look to see if this data now here changes. I haven't tried it. Okay, so we're in, let's go to normal mode. So let's go to a quiet, yeah, we're in normal mode. Okay, so we're going to run it. Here we go. So I press it. Let's press it again. Look, bingo, there we go. Wow, I could have saved like half an hour of video or something. Look, that's it. The bit is shifting exactly what I expected from the get-go. And like, why that's a problem with the Rohde Schwarz measuring its own clacker, I don't know. I honestly do not know. So now we can get in there and actually decode the bit. That's exactly what I expect. It's exactly as per the data sheet. Here it is. It's exactly what we expected with the 24 bits or whatever. Here we go. Write operation. There we go. It's supposed to send 24 bits, the command, and then the data field, and we have the data for that. And we can see the bit changing. Yeah, it's somewhere over here. Yep, if you correlate it, look, it looks to be in the right spot to have the D6, D7, and D8, which is our filter selection field. Alright, so let's just have a look at the first section, which is the command section here, and we'll just expand that out, and here's where it starts here, and the command to write is a 0. By the way, the read is a 1 there, so that's basically it. All the others don't care, so that's actually pretty wasteful. So anyway, it is 0 because it's the first transition, remember, after the chip select goes low, which it has done, which is way off screen. It does it sometime before that. Then the first positive edge there is, and the data is a 0. So we are in write mode, so it is writing, and now we can, and all these bits are zeros, they're all don't care, so then we have to figure out where the next bits go. Okay, so this first high here is actually, if you count the positive edges there, unless I'm wrong, then that is the 14th count. So we've already got the first 8 bits are the command word, so it'd be 9, 10, 11, 12, 13, and 14 here. So the first 1 bit there is we're looking at the full power. So it's not in full power mode. It's obviously in aux high Z mode. You'd have to look at the data sheet to know what that does. We don't care about that. We're after the filter. So The next bit is 0. Sure enough, it is. And then, ta-da, here we go. It's this bit, and this bit. So we've got 0, 0, 1. Let's have a look down here. 0, 0, 1. Wow. What do you know? Surprise, surprise. 0, 0, 1. 20 megahertz bandwidth. No worries. And what I'll do here, just because I can, I'll actually line up the waveform with this on the screen here. And that can just be a handy way to actually do it. And the way you do this is with your horizontal. Here, this is one of your uses for your fine horizontal control. So you go in there, and because if you don't do that, then you've got these huge big jumps, right? Your typical 1, 2, 5 sequence. But if you go in there fine, you can actually adjust this and move it across and all that sort of stuff. And we said before that that bit was, maybe I should stick the paper there, but we said that that first bit lined up with that one there, and you just scale it to match. So there you go. That's not actually too far out. We could tweak it a little bit better. It doesn't help that these things are not even like D10 is like the width there. Anyway, we can see that this transition here, this would be D6 down here. That's what we got, 0, 0, 1. And then D5, it just squeezes in. That one's a 0, as it should be. And LG and HG mode, I can't recall what that is. We'd have to read the data sheet. That's a 0, so we're in LG, whatever that is. And see table 7. This is the ladder attenuation field. So this value here is going to change based on the attenuation setting and what's required for the front end. So that won't change if we just change the bandwidth or anything like that. But when we change the volts per division setting for channel 2, we'd expect this data here to change. So we know that chipset is definitely being used for the 20 megahertz bandwidth attenuation, which is exactly what you expect. There's no other hardware in there. You don't have to examine any of the rest of the front-end circuitry to know that the 20 megahertz bandwidth limit is being done inside this LMH chip. So now we'll undo the bandwidth. So remember, my one is software licensed to 300 megahertz. Okay, so we want to see what that goes to. Will it go to full bandwidth, or will it go to the 350 meg bandwidth setting? Only one way to find out. Here we go. I'll hit it, and there we go. I can jump back and forth between those, and because we're triggering on exactly the same point, this is really neat. All right, we'll be able to see it. So what we've got is we've got 1, 1, and 0. Okay, so 1, 1, 0. Let's have a look. What's 1, 1, 0? 1, 1, 0. Oh, look at that. 750 megahertz. Wow, there's one there for full, so it's not 0, 0, 0, but they're certainly not setting it to 350. So obviously, because mine is a 300 megahertz bandwidth scope, that's the maximum in this range. Obviously, the 300 megahertz bandwidth is being done elsewhere, like in the rest of the front end is only capable of 300 megahertz. So they're actually capping it there. But you can bet your bottom dollar that the 200 megahertz version and the 100 megahertz version of this scope would enable those bits there. 99.9% sure. So there you go. That's interesting to know. Obviously, they've put it to a limit. Maybe 750 just takes the edge off something, perhaps, rather than just the full bandwidth, because I think this chip's capable of like 1 gig or something ridiculous like that. So, yeah, it's interesting to know that they've chosen 750 and not 650 and not 350. I can probably understand why they didn't choose 350. Maybe that would have an impact, some of the roll-off there, and it's issues, to do with pulse response of the front end and everything else. So, there you go. It's set to 750 megahertz. Right, so let's now see if this ladder attenuation changes here when we change our volts per division setting. It may not change on every setting, but let's give it a whirl here. And, whoa, hello. That's significantly changed. I did not expect... Oh, no, I think maybe our timing is out, is it? I'm not sure. I'm changing the time base range there. I would have expected everything here to remain the same, all of the bandwidth stuff. But It's not. That's interesting. The bandwidth could change, by the way, right down to like 1 millivolt per division or something like that, but I'm going up to 2 volts per division. Something else is happening. So let's have a look at that. There we go. That's better. That's a better look at it. Well, this is interesting. Look, we're getting no chip select now. When I do that, where's our chip select gone? But let's do the bandwidth. The bandwidth does do the chip select. And that's the invert button. I'm hitting the invert. Aha! Look, we're getting that. Are we getting that extra packet there? What's going on? Hang on, I'll single shot capture that. Bingo! Look at that. So the invert is doing 2 writes there with no chip select. That is interesting. Surely you need the chip select to also do the read. You have to. But I do find it rather fascinating that that's a hell of a lot more than 24 cycles, but both of these are supposed to be 24 read and write to this serial interface. This 3-wire SPI are supposed to be 24 cycles, and we're getting a lot more than that. My only conclusion is that there's something else on the bus. The chip select is not going low there. So this chip is not being selected. This data is not destined for this chip. Another one which we could capture perhaps that is doing the chip enable. There we go. So we need to actually trigger on the chip enable to get this. Okay, I'm now triggering from channel 1 and bingo. There we go. That's the only data that matters. So there's the only other conclusion, part B, the only other conclusion is that there are other chips on this bus, hence why they're using the 3-wire interface with the tri-state ability, because only this LMH chip is being accessed here, and that is the data. So that's actually the data. That's actually the data that we want to look at for the front end, okay? So let's call that up. There we go. Let's just have a look at it that way. And now I will change the time-based setting. There we go. There we go. You can see it changing, all those low order bits changing there. Yep, low order bits changing. So if I'm right down to 1 millivolt per division, 2, 5, 10, 20, there you go. And there's all our lower bits. All our lower bits changing to match that data table there for the ladder attenuation. So they are using the internal attenuators inside that chip as well as the bandwidth. So we have other chippies in there that are doing something all hooked onto the same bus. Oh, how annoying. That sort of, it was a bit of a red herring there for a little bit, but yep, easily figured it out. Trigger off the chip select, no worries. But that still doesn't explain why the chip select was not working on the Rohde Schwarz scope, on that logic analyzer, and because I was triggering on that thing and I could not get it. It just was not happening. It was not there. So something weird. Yeah, I still don't understand that. But anyway, we found what we came here to find. So this video took far, far longer than I wanted it to take. Sorry about that, but a lot of unexpected things happening here, and I still want to investigate what the hell's going on with this thing. But anyway, what I wanted to determine is that was that filter being implemented in the LMH chip? And yes, it is exactly as it expected. No worries whatsoever, and the attenuation, all that sort of stuff. And almost certainly the bandwidth of these things with the license options is being set in the bits in that chip, and that's it. Unfortunately, I can't find an option to actually uninstall my 300 megahertz license here. If I was able to do that, then and revert back to the 100 megahertz base unit, we'd be able to verify that 100 megahertz option in there was actually being set, and you can bet your bottom dollar it is. That's how they're doing it, because they've got a 100 megahertz model, they've got a 20 megahertz model, they're engaging the 20 megahertz, so they're definitely doing it. It's working for your regular 20 megahertz bandwidth limit, so almost certain that they're engaging both of those, because we know it's the same hardware, and this 750 megahertz figure is being engaged, is being set. when on the full bandwidth for the 300 megahertz version of this scope. So that's interesting that you could actually get in here and hack this thing. It's a bit ugly, but you could if you wanted to. If you had the 100 megahertz low-end version of this scope, you could have a little micro on that bus that actually because it's not a full, like a proper SPI bus, you can't just like plug it in series with the bus, because there's other, as we saw, there's other chips here on the bus there, right? So you don't want to interfere with any of those. But what you could do is any time that you could sit, and the micro could sit there and watch it, it'd have to intercept the chip select line, of course. And then, but if it did that, you could actually feed data on there to do that. But you'd have to make sure that you didn't conflict with any of the other data here, because you're writing onto a common data bus, which is clearly shared with something else. I don't know what. There's nothing obvious in the other front end. Some of the chips are not easy to identify, and yeah, I don't know what they're doing. So, but you've got to be careful not to overwrite that other data, because who knows what's going to be happening. But it's possible to actually get in there and just use, little man-in-the-middle attack, so to speak, and tweak those register settings to get yourself the full bandwidth scope. So there you go. I hope you found that interesting and educational, even if we did follow a few red herrings down a few rabbit holes there. It was fun nonetheless. So if you want to discuss it, leave comments down below, EEVblog forum, all the usual stuff. Hope you enjoyed it. Catch you next time.